Hello, my name is Eitan Kosman, and today I will present my joint work with Dotan Di Castro on vision-guided forecasting. This work was done during my internship at Bosch AI in Israel. It focuses on forecasting future states of vehicles based on history traces. Although much effort has been put into trying to estimate the state of a vehicle, learning to forecast the state of a vehicle introduces new capabilities, such as predicting dangerous situations. Moreover, forecasting brings new supervision opportunities by learning to predict a richer context expressed by multiple horizons. Intuitively, a video stream originated from a front-facing camera is necessary because it encodes information about the upcoming road. Besides, historical traces of the vehicle states gives more context. So, why do we need to forecast the future state of a vehicle in the first place? First, the average response time of a human driver is greater than half a second. Second, most of the driver's attention is focused on the front visual view, consisting of the route that the vehicle will pass through and the immediate future timestamps. This suggests that driving decisions are not made instantaneously, but rather done by short-time planning. This makes it highly valuable to predict the future state of the vehicle given the current measurements. Moreover, by forecasting we can avoid dangerous situations ahead of time by treating scenarios where anomalous behavior is predicted. Our solution relies on a model consisting of three modules: a video processing module denoted by MV, a controller area network signals processing module denoted by MC, and a fusion module for predicting the output sequences from both feature representations denoted by MF. The processing modules are fed with the inputs and encode them to compressed representations. The fusion module MF then performs multi-horizon forecasting. In the following, I will present three architectures that we developed for performing multi-horizon forecasting. In all our architectures, we keep MC and MV unchanged, while we change the structure of MF. The first architecture predicts each timestamp individually with a fully connected fusion module. The outputs of both MV and MC are flattened and concatenated, and the result is fed into a fully connected neural network with a relay activation between every two consecutive layers, which outputs predictions for a single timestamp. We duplicate and train this model for each timestamp to perform multi-horizon forecasting. The second architecture predicts multi-horizons simultaneously with a fully connected fusion module. Similar to the first architecture, the outputs of both MV and MC are flattened and concatenated. The result is fed into a fully connected neural network with relay activations between every two consecutive layers, which outputs predictions for all timestamps simultaneously. The third architecture predicts multi-horizons simultaneously via LSTM. We flatten the output of MC and concatenate it with the outputs of MV on the temporal dimension, creating a series of feature vectors containing both visual and signals data. The series is then fed into an LSTM module, followed by a fully connected decoder for predicting the values for all timestamps simultaneously. In the following, we describe how we evaluate the proposed models. The conventional evaluation protocol used in the literature is mean absolute error and root mean squared error. However, this protocol does not suit imbalanced datasets. We performed an experiment showing that a biased predictor, which outputs a constant value of 0, achieves a mean absolute error of 4.1 degrees on ConMyAI dataset and 6.9 degrees on Audacity. Although these errors are significantly higher than results of previous works that estimate steering angles, it can be considered as negligible because of the relatively high tolerance of the steering wheel, which has a wide range of values anyway. However, the biased predictor completely misses sharp angles, suggesting that the mean absolute error poorly quantifies the error. Moreover, a slightly worse error in these measures is forgivable if a predictor is able to perform well in the edge cases. Thus, we propose evaluating the prediction performance on a pair-range basis as defined by mean absolute error at alpha. For evaluation, we use two commonly used datasets. Both datasets include video frames recorded by the dashcam as well as sensor traces from the controller area network of the vehicles. During training our models, we perform augmentations in order to alleviate the imbalance of the datasets. First, we perform horizontal flips of the video clips with multiplying the steering values by -1. This prevents the model from leaning with steering angle bias towards one side. Second, we omit training samples with speed below 4 meters per second, as steering values in these situations are not informative and halt the training. We begin with the analysis of the experiment results of steering angle prediction provided in the following table. This table shows the error in terms of MAE and RMSE for the three architectures. The first conclusion is that we were able to predict the steering angles with great results for the steering estimation task. We also observe that the first architecture achieves the worst performance among the three, suggesting that multitask learning via multi-horizon forecasting quantitatively improves the results. Moreover, the third architecture that incorporates LSTM achieves better performance than the second architecture that doesn't incorporate LSTM. This implies that a sequence-to-sequence LSTM as a fusion module is beneficial. We continue with the analysis of the experimental results of speed prediction. Similar to the steering angle forecasting results, the first architecture achieves the worst performance among the three, while the third architecture achieves the best results. Following the success of the latter on both tasks, we conclude that performing multitask learning through multi-horizon forecasting and incorporating LSTM in the fusion module improves the performance. Additionally, we plot the graphs of MAE at alpha. Notice that the error growth for the third architecture is slower than the error growth for both first and second architectures. We conclude that the third architecture is more robust and is able to deal with the imbalanced distribution of the steering angles better. We experimented with multi-horizon forecasting without vision features in order to examine its impact on accuracy. Specifically, we choose the architecture that delivered the best results, that is, the third architecture, and omitted the video stem. The rest of the architecture remained the same. According to the result provided in the table on the left, the model using only non-vision features performs significantly worse, implying that the vision features have significant positive effect on the performance. In addition, the figure on the right shows the graphs for MAE and alpha for both configurations on both datasets. Notice that the error for the experiments that do not use vision as input, as depicted in Figure 10a and Figure 10c, the error grows dramatically faster than the experiments that use vision features depicted in Figure 10b and Figure 10d. With this, we conclude that using video clips as input for our models allows it to cope with the imbalanced distribution of the steering angles in both datasets.